let me just give a brief introduction of this session. So my name is Nuno. I am a postdoc at the Tohoku University. And with me today, I will have a co-chairing the session, Galen from Virginia Tech. And also Junyi Wu from the University of Illinois in USA. And the first session will be started with Troy Dion. So he's our invited speaker. Troy did his PhD at UCL in London, and he is now an assistant professor at Tohoku University, so the same place where I am. Just to give a brief bio, from Troy is working on artificial spin ice, and in an array of assistant interacting nanomagnets, where the properties are tailored by the geometry and the magnetic state. So Troy will be talking about this today. So his title will be A Brief History of Artificial Spin Ice from Differential Fabrication to Application. And Troy, can you try sharing your screen?
Sure, yeah.
Great. So before we start, I just want to give a brief idea of how to ask questions during the session and the next ones. So don't unmute yourself during the talk. You can ask the questions during the chat, and then we will read them to the speaker afterwards. Or if some other question comes up and you want to speak, just raise your hand in chat, and if there is time, we will allow you to speak. So Troy, please go ahead. Thank you.
Great, thank you. Thanks for the introduction, and thank you to all the organizers for giving me the opportunity to speak today. And also thank you to my collaborators, which span across Imperial College, University of Delaware, Colorado Springs, Kyushu University, Tohoku, and UCL. So yeah, I'll be talking about kind of the history of my research in artificial spin ice. So yeah, I'll get started. So first, I'll just give a brief history of what is artificial spin ice and its history, where it comes from. And then I will talk about how we can manipulate the state in these systems using temperature or magnetic field, and then more specific tip writing techniques. And then I'll also talk, the main topic is the differential fabrication. And then the states that we're able to access with this technique have led to some interesting results, and those results have also led to some interesting applications. So that's the title of my talk. And then if I have time, I'll talk briefly about some future work in this space. Okay, so what is the history? So in water ice, in the 1930s, they tried to measure the thermodynamics of water ice, and they actually found it has a residual entropy at 0 degrees. So does this violate the third law of thermodynamics as we know it? So probably not, but why? So what's going on here? So ice forms this tetrahedral structure due to the hydrogen bonds. And if you look at this, this structure, we find that the two protons lie close to the central oxygen atom, while 2 will reside further away from it. So this is what's called the ice will, and this is the representation of the ground state of water ice. However, when you consider a large ensemble of these unit cells, this cannot be satisfied simultaneously, and this leads to a frustration. And because of the high degeneracy of these states, it leads to this residual 0-point entropy. But if you want to investigate the thermodynamics or the excitations in water ice, it's very difficult, because as soon as you try and probe water ice, it starts to melt. So are there other systems we can look to? So in the 1980s, they found that pyrochlor materials such as dysprosium titanate or holmium titanate also show this residual entropy behavior. In this case, there are magnetic moments, and they reside on the corners of a tetrahedra. They either point into the center or point out of the center. So they basically observe the exact same geometric rules. So they have the same kind of thermodynamic properties. And the fundamental spin excitations behave just like magnetic monopoles. So these are quasi-particles, not real monopoles, which don't exist in nature as far as we know, but they obey the same laws of physics as if they would. And these are connected by these Dirac strings, which are interesting topological objects. So now we have a system which is much more amenable to experimental investigation. However, it's still difficult because you have like a three-dimensional system and you're only able to look at natural compounds that have this property. So that's where artificial spin ice comes in. So because of lithographic techniques, we can fabricate very small nanomagnets, and these behave like icing spins, so they can point in one of two directions, and we can treat them as just a single spin. And then we can arrange them in this square lattice, and it obeys similar thermodynamics as the three-dimensional case. And imaging them is very simple. So this is a nice SEM picture, and we can use magnetic force microscopy, Kerr microscopy, or X-rays to image the magnetic state of these systems. So we now have a very easy way to see how the thermodynamics of these systems behave. So in the little side, the square artificial spin ice, there are 16 total configurations. However, because the adjacent islands are closer to each other than the opposite ones, they have a stronger dipole interaction. And this means that the ground state is actually split into two different energies. So you have this type 2 state, which is a slightly higher energy than the type 1 state. Then you have the excited states, the type 3 and the type 4. And these are just MFM simulations, so you can see how these things are configured. So the type 3 and the type 4 will have a net magnetic charge, whereas in the type 1 and type 2 states, the charges cancel out. So the original intention was to look at thermodynamics in artificial spin ice. So for example, in this study, they look at how annealing temperature affects the state. So they start with saturating the sample, and then they apply different temperatures and see what state it ends up in. And you can see in this image here, even when they anneal the temperature, you still have these dislocations. So this is resulting from the frustration, from this geometrical frustration of the artificial spin ice. People have also looked at the excitations, so these Dirac strings and monopoles. And also you can look at thermal fluctuations in these systems. But because we're using lithography and this is an artificial system, we're not stuck with just this square geometry. And it has a huge number of states, of course, but we can use many different geometries. So this is just an example of a few of those kinds of geometries that people are doing. People actually also make 3D structures to even better mimic the spin ices that they were first intended to model. But in recent years, one of the things that has drawn attention is the magnonic community. So magnonics is where you look at spin wave excitations, and magnonic crystals, for example, is where you can control the band structure of the material, control the band structure of the spin waves by changing the material, the geometry, or even the magnetic state. So by changing the magnetic state of the material, we have a reconfigurable way to change the band structure of that material and change how the spin waves will propagate through that material. So that means magnetic state manipulation is important. So how is that achieved in artificial spin ice? So we can actually do this AFM tip writing. So we take a atomic force microscopy tip with a highly magnetized tip, and we can drag it across one of our nano islands, and it induces these topological magnetic defects, which create these two domain walls, which then move to the ends of the wire, and then you end up with a magnetization reversal. This is a very difficult technique. It's very cumbersome. You have to have an AFM, so it's not the most elegant way to do this if you want to do some kind of application with it. But there are also, Killian Stenning at Imperial College has developed this optical switching. So you can use a laser, a polarized laser to switch elements. There are also, you can apply demagnetization protocols where you just do like an AC magnetization, AC demagnetization where you reduce the field and you can reach the ground state, but what about all the other states that we want to have access to? So the question is there a simple and more effective way to write states using global magnetic fields? And this is where the differential fabrication comes in. So the coercive field, or the switching field of these magnetic nanoislands, it strongly depends on the shape anisotropy. So as you make these elements smaller and smaller, the field you need to switch these things gets larger and larger. So if we apply a magnetic field along this direction, which nanomagnet will switch first? So you'll see that the wide one is going to switch very quickly. And then it takes more and more field to reverse the thinner and thinner islands. So we can create this staircase ASI where we, along one of these diagonals, well, actually every other diagonal, we have this staircase. And what that allows us to do is to access all the states. So if we apply a large magnetic field in this direction, we reach this type 2 saturated state. And then depending on the magnetic field direction, we can determine the resultant ASI state after we apply magnetic field. So if we apply the magnetic field along this direction, these two perp ones have reversed. So because they've got a lower coercive field, they will switch before the other two. So these remain fixed. And now we've reached the type 1 state. If we apply the field along this direction, then these two will switch. And now we've reached the type 4 state. And then if we apply the field at a slight angle, we can reach the type 3 state. So now we have access to all the states in the artificial spin ice just by simply changing the width of a subset of the bars. So this is the essence of differential fabrication. So because we're trying to aim for some kind of application rather than modeling the thermodynamics, we don't really care about the homogeneous nature of the ASI anymore. We can now access those states. But it's all very well. What I've shown you here is just simulation. Can we achieve this experimentally? And the answer is yes. So these are magnetic force microscopy images of pure type 1 to type 4 states. So here you can see the type 1 and here the type 4. But as many of you will know, magnetic force microscopy is a very slow technique. So how do we distinguish these states more rapidly in a way that we can apply in some kind of device? So typically we use ferromagnetic resonance. So I'll quickly describe this for those who are unfamiliar, but essentially the magnetization dynamics of magnets are described by the Landau-Lifshitz-Gilbert equation. And this basically describes the precessional motion of a magnetization vector around some effective field. And this effective field is a function of the externally applied field, in our case, the shape anisotropy of the islands, and then dipole field from neighboring islands. And the frequency of the precession is proportional to this effective field. So by injecting microwaves into magnets, we can measure the dynamics. So for example, if we have a very thin magnet, it'll have a high frequency. So you'll see that this one will resonate when it's at a high frequency. And then we have the wide magnet, which will resonate at a lower frequency. So essentially, this gives us a fingerprinting tool. And because of the differential fabrication, it breaks the degeneracy of each state. So by applying the field at a slight angle, the FMR spectra for all of these different states is unique. So this is a very effective fingerprinting tool for finding out what the state of your artificial spin ice is. And we did that experimentally for each of the states. So here on the x-axis, these are actually preparation fields. So these are all actually measured in zero field. So we go up to this preparation field, go back to zero, and measure the ferromagnetic resonance. So we're ignoring any of the applied field contribution, and we're just looking at how the internal field of the artificial spin ice gives us the dynamics. So we can distinguish all these different states. And here we can even see, like, we can see the proportion of, say, type 3 to type 4 that we have in our system by looking at the ratio of how that mode is changing as a function of field. Okay, so I think we were the first to measure this pure type 3 state. And what we noticed was that we have this kind of gap opening up in our dynamics. And so Akansha Sood, who is actually speaking after me today, at that time when we were both at UCL, she was working on synthetic antiferromagnets and coupling in those systems. And you actually can open up a gap. So these avoided crossings are actually evidence of strong coupling. And this requires an antiparallel magnetization component, which the type 3 state does. And this coupling was actually thought to be too weak in the artificial spin ice system. But it was actually because people weren't measuring in the right geometry. So previously, people would typically measure along one of the sublattices. And then one of your modes is going to look like this in the red. And then your other one's going to look like this. So there's actually no point where these modes would have a chance to cross, where you'd actually see evidence of this avoided crossing. But even in the case where you do apply the field between the two sublattices, if you're in this type 2 configuration where your field is along the same direction as the average magnetization, you do have a gap open up, but the damping in the systems is quite large if it's made from permalloy. And that means that you will not see this. So your two peaks will probably look like a single peak. So it was kind of overlooked. But if in fact you have your type 2 pointing in the vertical direction and you apply your field along the horizontal direction, you actually create the situation where you open up a gap. So not only so we wanted to test that it wasn't just this staircase ASI that was creating this gap, but we in fact showed that we do get this gap for a homogeneous square ASI as well. So what are these modes exactly? So if we have two moments with opposite magnetization, M1 and M2, so the resulting magnetization has two processional modes depending on the phase of M1 and M2. So if they process in phase, they form this acoustic mode. So you can think of this like a two-coupled pendula. When they oscillate in phase, they form this acoustic mode. But if they oscillate out of phase, they form this optical mode. And then if they're strongly coupled, there will be a gap between those two modes. And then we can define this normalized coupling rate as the gap frequency divided by the upper frequency. And this is just a 3D version of that. You see why this is called the acoustic mode, because it's like an acoustic phonon, whereas the optical mode is like moving transverse, so it's this out of phase optical mode. So then I did some simulations to see how we can increase this this gap size. So people generally want this coupling to be as strong as possible. And maybe unsurprisingly, reducing the distance between your magnets increases the coupling between them and also increasing the magnetic volume. So we want to know if we could push this gap into the gigahertz. But we're kind of pushing the limits of lithography of how close we can get these magnets. So the natural way to go is to actually go for multi-layered ASI. So now we have two ASIs growing on top of each other, where now the differential fabrication is happening with the thickness. So now we have a 20 nanometer one on top, 30 nanometer one on the bottom. So we can actually switch the top layer independently of the bottom layer. So we can create this anti-parallel state. So here from the hysteresis state, you can see it's kind of looks like a synthetic antiferromagnet. we can achieve this antiparallel and parallel phase. And the good thing about this is it can be in the parallel or the antiparallel state at zero field. So one other thing we can do is by making the islands wider, we can achieve a bistability between the macrospin state and these vortices state. So by increasing the number of layers and the width of the islands, we actually massively increase the possible microstates in this system. So the more states you have in your system, the more effective it can be used in, say, reservoir computing, which I'll talk a little bit about later. So what is the coupling in this system? So we simulated a basically decoupled system where we have a spacer layer that's very large, and we see that the two modes will cross each other without any evidence of an avoided crossing, so no coupling in this system. And as we reduce the distance between the two layers, we see that that gap gets larger and larger. And as I said before, we can calculate the normalized coupling rate. And in our system, based on our spacer thickness, we should achieve a several gigahertz gap. And that's what we do in fact find is a gap of around, 7 gigahertz. And then our colleagues, Benjamin Jungfleisch at the University of Delaware, used BLS to measure a single island. So this was to just a sanity check to ensure that the coupling is coming from the islands being on top of each other rather than neighboring islands. And we see, yeah, this gap is even occurring for a single island. So when we make these samples, we do this shadow depositions technique where we spin cut the resist, we expose, which leaves us with this slight overhang. We then deposit our magnetic material at an angle. And then for the spacer layer, we rotate the sample. And then for the second layer, we deposit in the opposite direction. And this leaves us with this slight offset between the top and the bottom layer. So this is not really differential fabrication, but it's some other kind of fabrication trick that we play. But why would you want this offset? So if we assume that our bottom layer is pointing in this leftward direction, we can create two different cases. We have a Y offset and an X offset. Now, if we consider the shaded regions where the top and the bottom layers are overlapping, and we also assume that the anti-parallel configuration is the lower energy, so it wants to be in this anti-parallel configuration, let's draw the arrow in the opposite direction on the top layer for these shaded regions. And then if we use these as the starting point of our vortices, then we find for the Y offset, we get everything anti-clockwise. But for the X offset, we get half of them anti-clockwise and the other half clockwise. So by creating this offset, the dipolar field from the magnet underneath generates an energy imbalance between the clockwise and the anti-clockwise vortex, which then gives us control over whether we have 0 or 50% of, 50% to 100% of either one of the clockwise or anti-clockwise. So this offset gives us control of the vortex chirality available in the artificial spin ice. So what's interesting about vortex dynamics in artificial spin ice? So in our previous work, there wasn't so much interesting in terms of the coupling. So you have this macro spin states, and then you have the vortex states, and they're kind of independent of each other. I will talk about later about how that was used for reservoir computing, but in terms of the coupling between these modes, there wasn't anything that we could see. Whereas when we look at our multi-layered ASI, so when we have macro spins in one layer and vortices in another layer, we notice that the macro spin mode has these additional higher and lower modes. And I thought, oh, that kind of looks like frequency combing. So we're all familiar with a laser, which has a single frequency, but a frequency comb has discretely regularly spaced frequencies around that carrier frequency. And this has applications in things like LiDAR, which was used to measure like exoplanets around different stars in other solar systems. It could be used for autonomous vehicles, geoscience, and parallel computing. So in parallel computing, it's used in optics, but they need a second device to create the frequency combing, and then that frequency comb goes into the system. In our system, if we could achieve the frequency combing not with a separate device, but from within the exact same system. So that would allow us to miniaturize a device more than you would be able to in optical versions of this frequency combing. And because our system already operates in the gigahertz, it's much more easy to integrate with existing telecommunications, which already work in that frequency. And then can we use this to increase the input of a magnetic reservoir computer? Or because of its metrology properties, its ability to correct. So essentially, because you have this large frequency comb, you can use the edge frequencies at the high and low frequency to correct for small changes in your carrier frequency. So it's basically a metrology tool, which is why it's been used for the applications I mentioned. So can this create a magnon-based quantum computer? But this magnon frequency combing is kind of a new field of interest. It's been discussed before in this paper where they look at a breathing skyrmion and they pass a spin wave through it, and then the spin wave interacts with the breathing skyrmion and it generates this frequency comb. Problem with this is they need a high threshold. I think they need a few hundred millitesla to achieve this, which is impractical in real experiments. So this is just a simulation paper. And then it's also been achieved in single vortex states, but you need to drive the core simultaneously to see this effect. So in our system, this video going to work? Yeah. So in our system, we actually look at the vortex core dynamics. So what's causing this frequency combing is the fact that the core of the vortex is moving in this elliptical shape. So it's generating a changing magnetization texture in the macrospin that's above it. And this change in the magnetization texture over time is what generates this ability to create this frequency comb. Excuse me. This is what the modes look like in the system. And this is yeah, so you can see that even when you're exciting the system off resonance of the vortex gyration mode, the gyration mode is so highly coupled to the macrospin above it that it's involved in the dynamics, and which is why it causes the frequency combing effect. Okay, so we can also tune the distance between the combs. So yeah, we kind of do this magnon dentistry, where you can see here the black line represents the frequency of the gyration mode, and then these are the distance of the separation between the teeth. So by increasing the field, we increase the gyrational frequency, which increases the gap between those frequency combs. And this is from the paper I mentioned earlier. They need 130 millitesla to actually get this frequency combing to kick in, whereas in our artificial spin ice, it happens at a more reasonable 1.12 millitesla. And if we include a second frequency at the gyration frequency and we increase the power, we can increase the effect. So we see more teeth of the comb occur when we also include a second frequency at the gyration frequency. Okay, so that's the frequency combing. So let's move on to some of the applications. So magnons are quasi-classical representations of collective spin excitations in magnetic materials. So I mentioned this earlier. We can control the spin wave dynamics and their propagation through materials by changing the underlying magnetic state. So there's this one where they use PMA materials and they change the configuration, and that changes how the spin waves propagate through. This is also another artificial spin ice study where they put artificial spin ice on top of some magnetic thin film, and then the artificial spin ice essentially acts as like a dipole field injection. So at the vertices of the artificial spin ice, the stray field will go into the magnetization of the thin film and change how the spin waves will travel through that magnetic thin film. So here I have some simulations of when we have a type 1 state, you essentially, all the charge here is cancelled out. So none of the stray field goes into the bottom layer. So you end up with just a dispersion of a magnetic thin film. Whereas if you have a type 4 state, you create this lattice of monopoles, and those monopoles will generate band gaps in the dispersion. So you can actually create band gaps by changing the magnetic state of the artificial spin ice. Okay, so reservoir computing is a kind of machine learning technique. So it uses a dynamical system to process time-dependent input signals. So basically you feed some input into a nonlinear system. So you have some linear input, you then change this nonlinear system, and then you get an output. And the advantage of this kind of scheme over other deep learning networks is you only need to do your training on the output layer. So essentially your reservoir is doing a lot of the work for you. And because you're not having to train every single layer in this middle section, which you would have to do with the deep learning algorithms, this is actually a lot more cost effective. Yeah, so the internal states, they respond in a complex and high dimensional way. So yeah, your training is only performed on the output. Yeah, and you exploit the natural dynamics of the reservoir rather than doing it computationally. So ASI has nonlinear dynamics, and it also has the fading memory, which is required. So it has to remember a few of its previous states, but it also has to forget states from a long time ago. And with magnetic systems, we have many ways of inputting signals. We can do field protocols, we can add spin torque, and then we can measure the output using, say, Hall voltages, MOC, or FMR. So reservoir computing in ASI was achieved with Jack Gartside and others. So as I mentioned before, we have this bistability where we have the vortex and the macro spin mode. So as we can do loops of fields. So we go to a positive field, then a negative field. And as we do more and more loops, we actually start to populate the system with more and more vortices, because the vortices are more robust to field. So they get generated, but they don't get turned back into macro spins. And this is a nonlinear process. So these sigmoid functions are basically what you need to be able to do any kind of machine learning. So we have some input, which is varied in time, and then that changes the dynamics of the artificial spin ice, and then we can measure the proportion of macro spins and vortices using FMR. And then on those outputs, we then perform the machine learning algorithms. And here you see with no vortices, we get bad future prediction. But if we include the vortices and the macro spins, we get this very good, excellent prediction. So ASI was used with these vortices to basically show that reservoir computing is possible in the system. Okay, so For future work, I mentioned how we have this MFM way of getting exact states, but it's very cumbersome. Not everyone has a AFM hanging around to set the state of their ASI. So we want to use spin transfer torque switching. And if we basically taking inspiration from MRAM to create these systems where we can switch the magnetization of the ASI using spin torques, and then we can rapidly read these states on a more individual level. So that's hopefully what I would like to see in the future. Okay, and just to summarize, I talked about the history of ASI and its use as thermodynamic toy model. And then the differential fabrication, I talked about state manipulation, the bistability of vortices and macrospin states, how ASI shows a strong coupling in the multi-layer system, and then how the vortex macrospins can generate frequency combing effects. And then I briefly discussed ASI as a reservoir computer and how it can control spin wave band structures for magnetic computing. Thank you for listening and happy to take your questions.
Thank you, Troy, for an amazing talk, as usual. So we have a couple of questions in the chat, so let's start with those ones. Olivia asked, on what kind of timescales do ASI states change under manipulation?
So typically, if you're talking about the magnetization reversal, that's on the order of nanoseconds. What was the second part of the question?
It says at what kind of timescales does it modify under manipulation, I guess, by field.
Yeah,
Olivia,
so so I guess, nanoseconds, so typical, just like magnetization reversal timescales. But then if you have, some people do like super paramagnetic artificial spin ice where you make them very thin, so then they can be manipulated by temperature, but I'm not sure what the timescales there are, but I imagine they're faster.
Okay. Then we have another question. He only has his phone number, so I don't know his name, but he says he has a basic question in square ice. Where is the frustration at the vertices? Because if I consider 2 in, 2 out, then is it frustrated?
Yeah, so it's easy, say, in Kagome spin ice to see where the frustration is, because in Kagome you have this hexagonal structure, and at the vertex you have 2 in, 1 out, or 1 in, 2 out. And there it's very easy to see because you have 2 interactions that are competing with each other. In the case where you have 2 in, 2 out, this square and the pyroclore, the frustration doesn't happen unless you have a large number of these states. And it's because there are many different ways to arrange them where the states are, the energy is the same. So it's a combination of the high degeneracy and the number of possible states. It's kind of hard to get your head around, I guess. But yeah, the frustration isn't in a single one. So if you have just the 4 magnets, you can arrange them in their ground state very easily. But as soon as you start adding more states, the more frustration starts to appear in your system.
Thank you. And he also asks, what is the minimum and maximum thicknesses of these kinds of ASI? I think it was the one,
Yeah, so as I mentioned, if you make them very thin, they start to thermalize, meaning that they will fluctuate with temperature, which some people do. So some people make them very thin, like on the order of nanometers. In that case, they're trying to use temperature to reach the ground state. They can go up to, it also depends on the width and the length of your islands. So if you make them very long and very wide, you can make them thicker. So essentially you want your thickness to be thinner than that. But usually we don't go higher than 30 to 40 nanometers, because once you start to go higher than that, then you increase the sort of out of plane effects, and it's perhaps not desirable. But yeah, usually from a few nanometers to few tens of nanometers is typical.
And there is Kumar that wants to ask a question, so I'm gonna allow you to speak. So you can speak if you want.
Hi, and thank you for allowing me to ask my question. So thank you for your nice presentation. So I have a simple question on the material choice. So
Yes.
how does the material choice influence the magnetic properties in ASI?
Yeah, it's a good question. So there's kind of two typical materials that people use. So the main one is iron nickel, so permalloy, and then the other one is cobalt iron boron. We tend to use soft magnetic materials so that the shape anisotropy is what dominates the magnetic behavior. However, there are some people that use PMA materials, so you can create perpendicular magnetized anisotropy materials, so they have kind of different interactions, but they're trying to achieve the same thing. Some people use I didn't really talk about it here, but I've just written a proposal where we're trying to reduce the field required by including magnesium oxide to reduce the shape anisotropy to, yeah, try and part I was talking about here. Yeah, so here we actually include this magnesium oxide, which will reduce the current needed to reverse these. So typically it's soft magnetic materials, but some people do other things if you want to change the properties slightly.
So basically the shape of the anisotropy, right? You focused on?
Yeah. So typically that's what people focus on, because you want the geometry and the arrangement to be the kind of thing that gives the material its properties rather than the material of the property itself. So that's why you would choose the soft magnetic material.
I see. So thank you for your answer.
Thank you.
Okay, if someone else wants to ask a question, please just raise your hand. In the meantime, I also have one question. Here is actually on this slide. So you want to do kind of magnetic tunnel junction as an ASI?
Yes, essentially.
Okay. And do you expect the same vortex dynamics? Because I know there is vortices when you do oscillators with MTJ.
In principle, I don't see why not. It would depend, yeah, on the thickness and the aspect ratio of your islands.
Okay.
But whether you can induce them or not with this spin torque, or whether it requires, the field, is probably. Is that what you were getting at?
Yeah, I know that you can put a permalloy on top of cobalt iron boron and below cobalt iron boron, so maybe you can get exactly the same thing. It's just to say that it's a very nice idea. And I also have a last question. When you are doing stacking,
Yeah.
if you keep going 3D, will you keep offsetting? If you want to stack another one on top, or there's no point?
Well, we can offset if we want to, but we don't have to.
Okay.
But yeah, I maybe about a year and a half ago, I was looking at like n number of layers and seeing what the thermodynamic of those thermodynamics of those systems look like, and basically because of the power nature, you get a huge number of states in a very small area. So that's like maybe something interesting to do.
That's nice. So one last question from Juni. So I think you can unmute. Yeah. Sorry. Yeah. I think you can unmute. I think I muted you by mistake. Yeah.
Okay, yeah, now I can talk now. Thanks for the interesting talk. I
Thank you.
actually have a follow-up question on this slide as well. I know for the MRAM kind of device, it is a little bit harder to scale up. And how do you envision like using an ASI in this kind of device? Like what's the successful rate for you to fabricating it like on scale?
Well, I don't think anyone's actually done this at low scale yet. So my kind of proposal is to first see if we can even switch one of these elements and then think about scaling. But yeah, I'm not quite sure.
Thank you.
Okay, so it's time to move on. Thank you very much, Troy, again, for the very, very nice talk. It was an amazing talk to start the AtC-AtG.
Thank you. Thanks for having me.
Of course. So please stick around and check the other talks because what's coming next is also very nice, of course.